The data coming out of our paleomagnetic labs this morning has completely shattered the timeline we thought we knew. For decades, we operated under the assumption that when Earth flips its magnetic poles, turning north into south, it is a relatively rapid geological snap, a chaotic transition lasting perhaps a few thousand years at most. But new analysis of sediment cores dating back 40 million years has just delivered a shock to the system. We are looking at evidence of not one, but two ancient polarity reversals that did not snap, but rather stalled, dragging on for up to 70,000 years. This is not a margin of error. This is a complete rewriting of the behavior of our planet's core. It suggests that during a reversal, the Earth does not simply switch polarity. It can effectively lose its primary shield for a duration long enough to encompass the entire history of modern human civilization 3 times over. This discovery fundamentally alters our risk assessment for the magnetic excursion we are observing right now. If a reversal is not a quick flip, but a prolonged collapse, we are talking about 70,000 years of exposure to relentless cosmic rays and solar wind. But before we panic about the future, we have to understand the anomaly buried in the past. The data comes from our high-resolution sediment cores that act as a magnetic tape recorder for the planet. As tiny magnetic particles settled on the ocean floor 40 million years ago, they aligned themselves with the magnetic field of the time and were locked in place as the sediment turned to rock. By reading these layers, we usually see a strong north orientation, a brief period of chaos, and then a strong south orientation. That is the standard model. However, the new readings show something impossible under the old theories. Instead of a clean transition, the data reveals a magnetic field that collapsed in intensity and then stayed collapsed. It stuttered. It tried to flip and failed, then tried again, caught in a chaotic loop that persisted for millennia. This creates a massive puzzle. We call it the stalled transition anomaly. The question is not just why the field flipped, but what force inside the Earth was strong enough to hold the dynamo in a state of suspended animation for 70,000 years. To grasp the magnitude of this, imagine a compass that doesn't point north or south, but drifts aimlessly or points toward multiple weak poles appearing at the equator, and imagine that state of affairs lasting for thousands of generations. This brings us to the immediate implication of the data. The magnetic field is our shield against space weather. When it is at full strength, it deflects the bulk of ionizing radiation from the sun and deep space. During a reversal, the field strength drops to a fraction of its normal power. We used to comfort ourselves with the idea that this vulnerable window was short. Now we are staring at data that says the window can remain open for a geological epoch. This redefines the relationship between our planet's core and the atmosphere above it. If the shield is down for 70,000 years, the solar wind has ample time to strip away lighter isotopes from the upper atmosphere, potentially altering the very chemistry of the air we breathe. If you appreciate deep analysis of these planetary shifts and want to ensure you are updated as we decode more of this geological history, this is the moment to confirm you are subscribed to the feed, as the data is evolving rapidly. We need to look closer at the specific magnetic signature found in these 40-million-year-old samples. The researchers found that during these ultra-long reversals, the field did not just weaken uniformly, it exhibited a terrifying instability. The intensity graph looks like the reading of a heart in fibrillation. It suggests that the geodynamo, the engine of molten iron swirling in the outer core, lost its coherent structure entirely. Usually, the Coriolis force organizes the flow of molten metal into columns that generate a dipolar field, meaning a field with two clear poles. But for 70,000 years, that structure dissolved. The Earth likely had 4, 6, or even 8 magnetic poles fighting for dominance. This multipolar chaos explains why the transition took so long. The system could not find a stable equilibrium. It is like a spinning top that begins to wobble, but instead of falling over, continues to wobble violently for an inexplicable amount of time. This observation defies our standard computer simulations of the core. In our models, the turbulent forces usually resolve themselves quickly. The fact that they did not implies there is a variable we are missing. There is a braking mechanism, or perhaps a source of interference, deep within the Earth that we have failed to account for until now. Let us consider the environment on the surface during the 70,000-year stall. With the primary dipole field collapsed, the magnetosphere would have retracted significantly. Today, our magnetosphere extends tens of thousands of miles into space, holding the solar wind at bay. During this ancient stall, the magnetosphere would have been crushed down toward the surface. High-energy particles that usually spiral harmlessly into the polar regions to create auroras would have been raining down across the entire planet. We are talking about auroras visible at the equator every single night for thousands of years. But these would not just be pretty lights. They would be visual evidence of high-energy radiation penetrating to low altitudes. The biological implications found in the fossil record correlating to this time period are subtle but telling. We do not see a mass extinction, which is surprising, but we do see stress. We see an uptick in the rate of mutation and adaptation. This aligns perfectly with a prolonged radiation exposure event. It forces us to ask a disturbing question. Is the evolution of life on Earth partly driven by these magnetic failures? If the shield drops for 70,000 years, every living organism is subjected to a higher background radiation count. This acts as a genetic pressure cooker. The new data suggests that our magnetic field is not a reliable constant, but a flickering candle that occasionally dims for durations that defy human comprehension. But here is the detail that truly unsettles the analysts. In the sediment layers corresponding to the middle of this 70,000-year period, right when the field should have been finding its new orientation, there is a sudden, sharp spike in intensity, followed by an immediate crash. It looks like a false start. The core tried to re-establish a dipole, generated a massive surge of magnetic energy, and then collapsed back into chaos. This surge indicates that the energy was there, but the organization was lacking. It is evidence of a failed reboot of the planetary dynamo. This specific pattern, the collapse, the long stall, the false start spike, and the final resolution, creates a fingerprint. And when we look at the magnetic data collected from satellites orbiting Earth today, specifically the data concerning the South Atlantic Anomaly, we begin to see uncomfortable parallels. We are seeing a localized collapse in field strength and a drift of the magnetic poles that is accelerating. If the ancient pattern holds true, we are not just heading for a flip, we are heading for a stall. The difference between a flip and a stall is the difference between a bad weekend and a century of darkness. The sheer duration of these ancient reversals forces us to rethink the interaction between the core and the mantle. The core is the generator, but the mantle is the container. If the container has irregularities, it can affect the flow of the generator. The 70,000-year duration is too long to be a simple fluid dynamics issue within the liquid iron. It points to something thermal, something strictly geological, that was preventing the field from locking into place. We are looking for a culprit that operates on a slow, grinding timescale. This brings us to the concept of heat flux. The magnetic field is generated by heat escaping from the inner core, through the outer core, and into the mantle. If that heat flow is uniform, the field is stable. If that heat flow is disrupted, the field goes haywire. The 70,000-year stall suggests that 40 million years ago, something blocked the heat. It suggests that parts of the lower mantle might have acted as a thermal blanket, trapping heat in the core and preventing the convection currents necessary to generate a strong magnetic field. If the heat cannot escape, the dynamo slows down. The engine creates less power. The shield fades. This hypothesis matches the data from the sediment cores perfectly. A slow suffocation of the magnetic field, driven by a clogged heat exhaust system in the deep earth. This is a terrifying prospect because we cannot see the core mantle boundary directly. We can only infer its state from seismic waves and, crucially, from the behavior of the magnetic field itself. The new data tells us that the condition of the mantle can dictate the safety of the surface for tens of thousands of years. As we analyze the fine-grained details of the sediment, we can actually measure the angle of the field relative to the horizon. In a normal, stable field near the equator, the field lines are roughly parallel to the ground. Near the poles, they are vertical. During the 70,000-year stall, the inclination data goes completely random. In one layer, representing perhaps a century, the field is pointing straight up. In the next layer, it is horizontal. In the next, it is pointing down. This rapid fluctuation in direction, combined with the low intensity, would have made navigation impossible for any creature that relies on magnetoreception. Birds, sea turtles, and even certain bacteria would have been flying blind, their internal compasses spinning wildly as the planet's field thrashed about. We must also address the recovery phase. How did the Earth finally snap out of this 70,000-year trance? The data shows that the recovery was surprisingly abrupt. After millennia of chaos, the field strength surged and the poles locked into their reversed positions within fewer than 4,000 years. This asymmetry is striking. A long, slow collapse, a massive, unparalleled stall, and then a sudden recovery. It implies a threshold was reached. Perhaps the thermal blockage in the mantle finally cleared, or a plume of hot material broke loose, restoring the convection currents. This abrupt recovery after a long stall provides a crucial clue. It tells us that the Earth's dynamo has a tipping point. It can be suppressed for a long time, but once the suppression is lifted, it roars back to life. However, for the life forms existing during the stall, the recovery came thousands of generations too late. They lived and died on a planet that was fundamentally different from the one we know today. A planet with a sky that glowed with radiation and an atmosphere that was slowly leaking into space. The implications of this extend beyond just biology. We have to consider the atmospheric density. We know that solar wind adds energy to the upper atmosphere, causing it to expand and then get stripped away. Over 70,000 years of weak shielding, the cumulative loss of oxygen and water vapor could be measurable. While it was not enough to sterilize the planet, it certainly altered the atmospheric pressure and composition. We are looking at a mechanism that regulates the habitability of the planet over deep time. The researchers who published this study are calling this the chronometric crisis of paleomagnetism. They have highlighted that many previous studies might have missed these long stalls because the sampling resolution was too low. If you only look at a rock every 10,000 years, you might see a North Pole, then a South Pole, and assume a quick flip occurred in between. It is only by sampling every few centimeters, representing much shorter time intervals, that the horrifying duration of the transition becomes visible. We may have missed dozens of these long stalls in the geological record simply because we were not looking closely enough. This realization creates a sense of urgency. We need to go back and re-examine cores from other reversal events. Was the Lesham event 41,000 years ago a stall or a snap? What about the Brunias-Matuyama reversal 780,000 years ago? If stalls are the norm rather than the exception, then our entire probabilistic model for the next reversal is wrong. We are betting on a quick transition, but the house odds now favor a long, drawn-out collapse. The sheer volume of data locked in these cores is staggering. Each grain of magnetite is a witness to a day when the magnetic North Pole might have been in the Sahara or the Pacific Ocean, or nowhere at all. The consistency of the stall signal across different samples confirms that this was a global phenomenon, not a local anomaly. The entire planetary field was suppressed. But here is where the story gets even darker. We know that the magnetic field protects us, but we often forget that it is generated by the turbulent, violent motion of molten metal. For that motion to stall for 70,000 years, the turbulence must have changed character completely. It suggests that the liquid core can enter a state of stratified flow, where the layers of metal slide over each other smoothly rather than churning. Smooth flow creates no magnetism. This is called a non-convective state. If the core goes quiet, the shield dies. The mystery that remains, and the one that keeps geophysicists awake at night, is what triggers the core to go quiet. We have established that the timeline is 70,000 years. We have established the intensity collapsed. But the physical trigger for this massive planetary hesitation is still obscured by thousands of miles of rock. We see the symptom, which is the stalled flip, but the disease lies deeper. As we stare at this data, a discrepancy begins to emerge. The thermal models of the core suggest that it should be cooling down over time, which theoretically should make the field weaker and reversals more frequent. Yet, 40 million years ago, the Earth was hotter. The core should have been more vigorous. Why then did it produce such a lazy, stalled reversal? This contradicts the thermal history models. It implies that heat is not the only factor. There must be a chemical or physical structure in the deep earth that acts as a brake on the dynamo, something that can turn a quick flip into a 70,000-year ordeal. And as we look at the seismic tomography of the deep earth today, we see massive, dense blobs of rock sitting at the boundary between the core and the mantle. We call them large, low shear velocity provinces. They are continent-sized mountains of rock deep underground. Could these structures be the culprits? Were they in a different position 40 million years ago? The correlation between the location of these deep mantle anomalies and the behavior of the magnetic field is becoming the most critical area of study in geophysics. Because if these massive structures influence the magnetic field, and if they are moving, then the magnetic future of our planet is tied to the slow, churning drift of solid rock in the mantle. The connection is tantalizing. The sediment cores give us the timeline. The seismic scans give us the structures. But to link them, to understand how a blob of rock in the mantle could hold the magnetic field hostage for 70,000 years, we have to simulate the physics of a collapsing shield. We have to understand what happens to the energy when the dynamo stalls. It does not just disappear, it transforms. And that transformation of energy deep inside the Earth might be the key to understanding why the reversal stalled. But to see that, we have to go beyond the sediment and look at the mechanics of the collapse itself. We have to ask what happens to a planet when its heart skips a beat, not for a second, but for an eternity. The answer lies in the interaction between the liquid core and the solid mantle, a battle of forces that we are only just beginning to comprehend. To understand the mechanics of this collapse, we must descend 3,000 kilometers beneath our feet to the jagged, uneven boundary where the rock of the mantle meets the molten iron of the outer core. This is the most dramatic physical frontier on Earth, a place where solid silicate rock rests upon a churning ocean of liquid metal that is as fluid as water but as hot as the surface of the sun. It is here that the energy transformation driving the magnetic stall takes place. We have long treated this boundary as a simple sphere, smooth and uniform, but seismic tomography reveals that it is actually a landscape of terror, filled with mountainous, inverted topography and vast, continent-sized blobs of dense, hot rock that dampen the flow of heat. These massive structures, known formally as large, low-shear velocity provinces, are the key suspects in the 70,000-year stall. We know there are two primary provinces today, one deeply anchored beneath the African continent and another beneath the Pacific Ocean. They act as thermal insulators. The geodynamo relies on the rapid escape of heat from the core into the mantle to drive convection. Hot iron must rise, cool against the mantle, and sink back down to create the loops of current that generate the magnetic field. But when these massive insulating blobs shift position, or when the flow of the liquid core rotates beneath them, they effectively place a lid on the boiling pot. The heat cannot escape efficiently. The convection currents grow sluggish. The distinct, organized columns of molten iron that generate the dipole field begin to falter and break apart into smaller, chaotic eddies. This is the physics of the stall. It is a thermodynamic chokehold. The core still has energy, but it is trapped, unable to vent into the mantle above. As a result, the magnetic field does not just flip, it dissolves. The energy that usually goes into maintaining a protective shield extending far into space is instead dissipated internally as heat and turbulence. During the 70,000 years identified in the sediment cores, the Earth was likely trapped in this exact configuration. The heat flow was stifled by the mantle architecture, preventing the dynamo from reorganizing itself into a new stable polarity. This suggests that the reversal process is not entirely controlled by the core itself, but is dictated by the slow, grinding tectonic shifts of the mantle above it. We are living on top of a system where the roof dictates the behavior of the engine. When the dipole collapses, the protection does not vanish entirely, but it changes shape in a way that is disastrous for the surface environment. In a standard dipole field, we have two poles, north and south, and the magnetic field lines arc high above the equator, trapping high-energy particles in the Van Allen radiation belts well away from the atmosphere. But during the stalled transition, the field becomes multipolar. We might see a weak North Pole emerge over Siberia, a South Pole over the Amazon, another North Pole near Antarctica, and a South Pole over the Indian Ocean. These localized poles fight one another. The field lines no longer arc high into space. They connect these local poles in short, tight loops that hug the surface of the planet. This multipolar geometry spells catastrophe for planetary shielding. The Van Allen radiation belts, which usually act as a reservoir for charged particles, are destabilized. They can be pushed down into the upper atmosphere or dissipated entirely. This allows the solar wind, a stream of protons and electrons moving at hundreds of miles per second, to slam directly into the ionosphere. This is where the chemistry of the air begins to change. When high-energy solar protons hit the nitrogen and oxygen atoms in our upper atmosphere, they do not just bounce off. They shatter the atoms. This process, known as spallation, creates a cascade of secondary radiation. We must visualize this as a particle billiards game played on a planetary scale. A single cosmic ray hits an air molecule, blasting it apart and creating a shower of neutrons, muons, and radioactive isotopes like carbon-14 and beryllium-10. In a strong field, this happens only near the poles. During the 70,000 years stall, this was happening everywhere. The entire sky, from the equator to the Arctic, became a permeable membrane. The production of beryllium-10, which we use as a proxy in the ice cores to measure solar activity, skyrocketed. This isotope physically rained down out of the sky, settling in the ice and sediment, leaving a chemical signature of the radiation storm. The atmospheric consequences of this prolonged exposure are profound. The influx of high-energy particles causes the ionization of the upper atmosphere to increase dramatically. This creates nitric oxides, chemical compounds that act as potent destroyers of ozone. So, while the magnetic field is down, allowing radiation in, the secondary chemistry is actively stripping away the ozone layer, which is our primary defense against ultraviolet light. It is a double impact event. The magnetic shield fails, and the chemical shield is eroded from the inside. This brings us to the question of atmospheric loss. We look at Mars and see a dead red planet that lost its atmosphere because its magnetic dynamo died billions of years ago. Earth is larger, with higher gravity, so we do not lose our air as easily, But during a 70,000-year window of weakness, the solar wind can inflict significant damage. This process is called sputtering. The solar wind transfers kinetic energy to atmospheric particles, giving them enough speed to escape the gravitational pull of the planet. Over a few centuries, this loss is negligible. Over 70,000 years, it becomes a measurable erosion of the planet's volatile inventory. We are talking about the slow bleeding of water vapor and oxygen into the vacuum of space. While it was not enough to suffocate life, it certainly reduced the atmospheric pressure and altered the heat retention capacity of the planet. We often wonder how life survives these events. If the radiation levels at the surface increase, surely we should see mass extinctions. The fact that we do not see a sharp extinction line at the 40 million year mark suggests that life is resilient, but it does not mean life was unaffected. We have to consider the difference between acute lethality and chronic stress. A stalled field does not fry the planet instantly. It increases the background mutation rate. It increases the incidence of cellular damage. It forces organisms to repair their DNA more frequently. This is an energy tax on life. Every organism on Earth would have had to divert metabolic energy from growth and reproduction to cellular repair. This creates a subtle evolutionary filter. Organisms with robust DNA repair mechanisms would thrive. Those living in deep water or in burrows would be shielded. But surface-dwelling megafauna, or organisms that rely on delicate food chains in the upper ocean, would face 70,000 years of heightened difficulty. We see shifts in plankton populations in the sediment record that align with these magnetic anomalies. These microscopic creatures are the foundation of the marine food web, and they are particularly sensitive to ultraviolet radiation. If the ozone layer was thinned by the magnetic collapse, the phytoplankton at the surface would have been decimated, forcing a restructuring of the entire ocean ecosystem. The behavior of the solar wind during this time creates another layer of complexity. The sun is not a constant light bulb. It goes through cycles of violence. Every century or so, the sun releases a massive coronal mass ejection, a billion-ton cloud of plasma hurling toward Earth. Today, our magnetic field catches this plasma and funnels it to the poles, creating a geomagnetic storm that might disrupt a few power grids. During the stall, however, a direct hit from a coronal mass ejection would not have been deflected. The plasma cloud would have wrapped around the planet, compressing the atmosphere on the day side and stripping it away on the night side. The surface of the Earth would have been bathed in induced electrical currents. If we look at the rock record, we can see evidence of these intense solar storms penetrating all the way to the ground. The presence of specific radioactive isotopes in rocks that were exposed at the surface 40 million years ago confirms that the ground itself was being bombarded. This changes our understanding of the terrestrial environment. It wasn't just the air that was radioactive. The surface soil was accumulating a higher load of cosmogenic nuclides. For 70,000 years, the Earth was effectively glowing in the ultraviolet and X-ray spectrum when viewed from space. We have to ask a critical question here about the recovery mechanism. If the mantle blobs were choking the heat flow, how did the core eventually break free? The sediment data shows that the recovery was sharp and violent. This implies a pressure buildup scenario. As the heat trapped in the core increased because it could not escape, the temperature differential eventually became so high that it forced a breakthrough. It is possible that a new plume of hot material punched through the stagnant layer, restarting the vigorous convection necessary for the dynamo. This would have been a cataclysmic event in the deep Earth, a sudden reorganization of fluid flow that rebooted the magnetic engine. This reboot was not gentle. The spike in magnetic intensity that marks the end of the stall is significantly higher than the average field strength. The Earth didn't just return to normal, it overcorrected. The dynamo spun up to maximum power, creating a super strong field for a brief period before settling down. This overshoot confirms the thermal buildup hypothesis. The core was running hot, and when the blockage cleared, it released that energy as a surge of magnetic power. But the most unnerving aspect of the physics is the randomness. The models suggest that during the stall, the poles were wandering across the equator at speeds of up to 1 degree per year. To a geologist, that is breakneck speed. To a navigator, it is chaos. If you stood on the equator during this time with a compass, the needle might point east 1 year and then drift to the southeast the next, eventually swinging around to the west over the course of a human lifetime. There was no true north. There was only a shifting local magnetic vector that offered no reliability. This directional chaos would have devastated migratory species. We know that birds, turtles, and even whales use the magnetic field to navigate. If the field is weak and multipolar, their internal maps become useless. They would have stranded themselves in massive numbers or failed to find their breeding grounds. The 70,000-year duration means that evolution had to step in. Species either abandoned magnetic navigation, adapting to rely solely on the sun and stars, or they went extinct. It is highly probable that the migratory patterns we see today are relatively new inventions, relearned by species after the field stabilized. There is also a sound associated with this phenomenon, though not one we can hear with our ears. The interaction of the solar wind with the ionosphere creates low-frequency radio waves. During a strong field, these are the chorus and hiss we detect with satellites. During a stall, with the solar wind slamming directly into the atmosphere, the radio environment of Earth would have been deafeningly loud. The entire planet would be emitting a chaotic scream of radio static. Any biological sense that relies on electromagnetic sensitivity would have been overwhelmed by this noise. We must also consider the thermal expansion of the atmosphere. When the solar energy is deposited deeper into the air column because the shield is down, the atmosphere heats up and expands. This increases the drag on anything orbiting the planet. While there were no satellites 40 million years ago, this physics is critical for us today. A stalled field means the atmosphere puffs up, reaching higher into space. In a modern context, this would scrub the low Earth orbit clean of debris and satellites within months. In the ancient context, it altered the weather patterns. The distribution of heat in the upper atmosphere changes the jet streams and the trade winds. The climate models for this period show unexpected shifts in rainfall and temperature that cannot be explained by carbon dioxide levels alone. It is very likely that the magnetic stall altered the global climate by changing the way energy was distributed in the upper atmosphere. The correlation between magnetic field intensity and climate is a controversial but growing field of study. The theory is that cosmic rays encourage cloud formation. When the field is weak, more cosmic rays hit the lower atmosphere, ionizing particles that act as seeds for cloud droplets. A 70,000-year stall could have resulted in a 70,000-year period of increased cloud cover, cooling the planet significantly. This magnetic winter scenario aligns with some of the cooling trends we see in the paleoclimate record. It suggests that the core of the Earth and the climate of the surface are linked by a chain of subatomic interactions. As we analyze the hysteresis of the magnetic minerals in these cores, we see that the grains were magnetized in a low-energy environment. This is crucial. It confirms that the field didn't just change direction, it lost its power. The energy density of the magnetic field dropped by over 90%. This is the difference between a roaring bonfire and a dying ember. The Earth was effectively defenseless. The only thing standing between the surface and the vacuum was the mass of the atmosphere itself. This lack of magnetic pressure allowed the solar wind to shape the ionosphere into a comet-like tail. On the night side of Earth, the atmosphere would have streamed out into space, creating a visible plasma tail. If you were standing on the Moon 40 million years ago looking at Earth, it would have looked less like a blue marble and more like a ragged, glowing comet, with a halo of escaping gas and auroral light wrapping the entire sphere. The terrifying realization from this physical analysis is that the Earth system is capable of getting stuck. We assume the dynamo is self-correcting, but the existence of a 70,000-year stall proves that it is not. It can enter a metastable state of failure. It creates a condition where the forces generating the field and the forces destroying it are perfectly balanced, locking the planet in a vulnerable twilight. This equilibrium of failure is what truly scares the physicists. It implies that a stall is not an accident, but a stable mode of operation for the core. Now, we have to bridge this ancient mechanics to the anomalies we are seeing right now. We have spoken of the mantle blobs, the African and Pacific LLSVPS. We know they move, we know they change shape, and when we look at the modern data, we see that the South Atlantic Anomaly, that growing dent in our magnetic shield, is sitting directly on top of the African Large Low Shear Velocity Province. The same geological architecture that likely caused the 40 million year stall is currently active and interacting with the core beneath the South Atlantic. This is not a coincidence. The weakening we measure today, the splitting of the South Atlantic Anomaly into two separate lobes, mirrors the multipolar chaos we see in the ancient sediment records. The physics of the past is becoming the physics of the present. We are seeing the early symptoms of a core that is being stifled by the mantle. The heat flow is being disrupted. The convection is stuttering. The question is no longer if the field can stall. We know it can. The question is whether the anomaly growing beneath Brazil and the Atlantic Ocean is the precursor to a quick flip or the beginning of a 70,000-year collapse. To answer that, we have to look at the rate of change. We have to look at how fast the field is deteriorating today compared to the resolution of the ancient rocks. And when we overlay the modern decay curve onto the ancient stall data, the lines do not just cross, they align. We are observing a trajectory that points away from stability. The core dynamics are shifting into a low-intensity mode. The shielding efficiency is dropping, and as we continue to pump electricity through global grids and rely on satellite navigation, we are marching blindly into a geophysical regime that this civilization has never experienced. The mechanism of the collapse is in motion. The mantle is squeezing the core, the dynamo is struggling, and the radiation waiting outside our gates is timeless and patient. But to understand the true immediacy of this threat, we have to turn our eyes away from the core and look at the monitors watching the sun today. We have to understand how a weakened field interacts with the modern solar cycle and what the data from our latest satellite constellations is telling us about the thinning of the veil. The ancient rocks have given us the warning, but the satellites are giving us the countdown. And the numbers they are sending back are defying all our standard prediction models. If we are indeed entering a stall, the timeline of humanity is about to intersect with the timeline of geology in a violent way. We need to know if we are facing a century of trouble or a millennium of darkness. The answer lies in the coupling of the new core data with our space weather forecasts. This is where the deep past meets the immediate future. This is where we see if the shield will hold. The anomaly is not coming. It is here. When we turn our satellites toward the South Atlantic, specifically the Swarm constellation deployed by the European Space Agency, we are not looking at a stable shield. We are looking at a wound in the magnetosphere that is widening with terrifying speed. This region, stretching from Brazil across the ocean to Zimbabwe, is currently experiencing a dramatic drop in magnetic intensity. We call it the South Atlantic Anomaly, but that name is too clinical for what it represents. It is a physical hole in our planetary defense system where the radiation belts act less like a shield and more like a sieve. And if we overlay the data from the 40-million-year-old sediment cores onto the daily readings from this modern anomaly, a chilling pattern emerges. The ancient stall began exactly like this. We are seeing the field strength in this region drop by roughly 5% per century, which is far faster than the background rate of decay. But more disturbingly, the anomaly is splitting. Just as the ancient sediment records showed a field fracturing into multipolar chaos, the South Atlantic Anomaly is currently dividing into two distinct lobes. One center of minimum intensity is forming over South America, and another is drifting eastward over Africa. This bifurcation is the hallmark of a dynamo that is losing its coherence. It suggests that the dipole, the two-pole system that has guided humanity for all of recorded history, is beginning to fray at the edges. This brings us to the most critical question of our time. Are we witnessing the start of a standard reversal, a quick geological flip that will resolve itself in a few thousand years? Or are we entering the precursor phase of a 70,000-year stall? The difference is existential. A quick flip is a crisis for our power grids. A 70,000-year stall is a fundamental alteration of the human condition. If the current decay follows the trajectory of the ancient anomaly, we are not facing a temporary glitch. We are facing a permanent reduction in planetary habitability that will persist for thousands of generations. We must consider the immediate technological impact of this weakening. Our civilization is built on a foundation of delicate electronics and global positioning systems that assume a strong magnetic field. The South Atlantic Anomaly already causes glitches in satellites that pass through it. The Hubble Space Telescope literally has to shut down its sensitive instruments when it orbits over this region to avoid radiation damage. This is the canary in the coal mine. If the field continues to weaken and the anomaly expands, this zone of exclusion will grow. We will see a breakdown of low Earth orbit infrastructure. The Starlink constellations, the weather satellites, and the spy networks will face a cumulative radiation dose that exceeds their design specifications by orders of magnitude. We are looking at a future where the cost of maintaining a satellite fleet becomes prohibitive because the replacement rate is too high. But the danger on the ground is far more visceral. We have to talk about the grid. The modern electrical grid acts as a giant antenna. When the magnetic field is weak, a solar storm does not just create pretty lights. It induces massive geomagnetic currents in the ground. These currents flow up into our transformers and melt the copper windings. In a strong field scenario, we can weather most solar storms. In a stalled, weak field scenario, a moderate solar flare becomes a civilization resetting event. The ancient stall tells us that the field can remain in this vulnerable state for 70,000 years. We cannot harden our grid for 70,000 years of constant bombardment. We would have to fundamentally redesign the way we transmit energy, moving from long high-voltage lines to localized microgrids, effectively deglobalizing our power infrastructure. This brings us to the speed of the magnetic North Pole. It is currently sprinting from the Canadian Arctic towards Siberia at over 30 miles per year. This is not the drift of a stable system. This is the erratic wandering of a system in flux. We have already had to update the world magnetic model ahead of schedule because the pole is moving so fast that NATO navigation systems were becoming inaccurate. This acceleration aligns perfectly with the onset of the ancient chaotic phase. The pole is unmooring itself. If the stall hypothesis is correct, the pole will not just move to Siberia and stop. It will cross the equator. It will fragment. We could wake up to a world where compasses in London point to a local pole in the North Sea, while compasses in New York point to a different pole in the Caribbean. Global navigation without GPS would become impossible, and GPS itself would be under constant threat from the ionospheric turbulence. The biological implications of a modern stall are even more unnerving. We discussed the evolutionary pressure on ancient life, but we are long-lived mammals with low reproduction rates. We do not evolve quickly. If the magnetic shield drops to 10% strength and stays there for millennia, the human population will be subjected to a chronic increase in ultraviolet and cosmic radiation. We are not talking about immediate radiation sickness, but a statistical increase in cancer rates, cataracts, and immune system suppression that becomes the new baseline for our species. We would effectively be living on a different planet, one with a harsher radiation environment. The atmosphere would technically remain breathable, but the upper layers would be chemically altered, stripping away the ozone and allowing more solar energy to reach the surface. This forces us to reevaluate our definition of a habitable zone. We usually look for planets with water and the right temperature. We rarely ask if their magnetic fields are currently stalling. The new data suggests that habitability is not a binary switch, but a sliding scale. During a 70,000-year stall, Earth slides toward the hostile end of that scale. The resilience of our technological society is brittle compared to the resilience of the biosphere. Life will adapt, but our electronics, our power distribution, and our satellite-based economies are not biological. They cannot evolve. They will simply fail. We must also confront the mechanism of the mantle. We know the South Atlantic Anomaly is sitting directly above the African Large Low Shear Velocity Province. This massive blob of hot rock is the smoking gun. It is the physical obstruction that is disrupting the heat flow from the core. The fact that the anomaly is growing suggests that the interaction between this mantle blob and the fluid core is intensifying. We are seeing the consequences of deep Earth tectonics playing out in the sky above us. If this mantle structure is indeed choking the geodynamo, there is no technology we possess that can fix it. We cannot restart the core. We cannot move the mantle. We are passengers on a geological vehicle that has developed a catastrophic engine knock. The terrifying reality of the 70,000-year timeline is that it removes the hope of a quick recovery. When scientists previously talked about reversals, they used terms like geologically instantaneous. That phrase gave us comfort. It implied that if a reversal started, our great-grandchildren might see the end of it. The new data erases that comfort. If a stall begins now, it will outlast the current languages we speak. It will outlast the ruins of our cities. It frames the current magnetic weakening not as a crisis to be managed, but as the onset of a new geological epoch. We are potentially the first generation to document the beginning of the long dark. We need to look at the link between this magnetic weakening and the climate. We know that the ancient stalls were associated with climate shifts. As the field weakens today, we are seeing changes in the upper atmosphere's temperature and density. The influx of cosmic rays affects cloud nucleation. While carbon emissions are the primary driver of current warming, the collapse of the magnetic field introduces a wild variable into the climate models. If the field creates a feedback loop that alters cloud cover or atmospheric circulation, our climate predictions for the next century could be drastically wrong. We might be preparing for warming while the magnetic field is preparing to trigger a distinct atmospheric shift that we do not yet understand. The most immediate danger, however, comes from the sun itself. We are currently approaching the peak of solar cycle 25. The sun is waking up. We are seeing X-class flares and massive coronal mass ejections. In previous centuries, the Earth's field was strong enough to shrug these off. But today, with the field weakening and the South Atlantic Anomaly expanding, we are playing a game of Russian roulette. If a direct hit from a massive solar storm strikes the planet while the anomaly is facing the sun, the damage will be localized but catastrophic. It could wipe out the power grid of an entire continent. The ancient data shows that during the 70,000-year stall, the planet was bombarded by these storms repeatedly. It was a shooting gallery. We have built a civilization of glass in a neighborhood throwing stones. There is a psychological dimension to this realization. For all of human history, the North Star and the magnetic north have been reliable constants. They are the metaphors we use for truth and direction. To learn that the magnetic north is not only movable, but capable of dissolving entirely. For 70,000 years shakes our sense of planetary stability. It reminds us that the Earth is not a finished product. It is a dynamic, violent, and indifferent system. The ground beneath our feet is a thin crust floating on a storm of liquid metal that can fail to protect us at any moment. As we deploy more sensors to the ocean floor and launch more satellites to monitor the field, we are searching for the point of no return. The researchers analyzing the sediment cores identified a specific threshold of intensity drop that signaled the start of the stall. We are dangerously close to that threshold in the South Atlantic. If the field strength drops another 10% in that region, the models suggest the chaotic multipolar phase will become self-sustaining. The dipole will not be able to reassert itself. We will have tipped the balance. The implications for future space travel are also profound. We speak of colonizing Mars, a planet with no magnetic field, but we are facing the prospect of Earth becoming more like Mars. If we cannot maintain a technological civilization on Earth during a magnetic stall, how can we hope to build one on a planet that is permanently stalled? This anomaly forces us to develop radiation-hardening technologies not for space exploration, but for survival right here on the surface. We may need to build our server farms underground. We may need to shield our hospitals and control centers with layers of lead and water. The architecture of the future might be dictated by the weakness of the magnetic field. We must also consider the silence of the data. There are huge gaps in our knowledge of the deep Pacific and the core dynamics beneath it. We are making these predictions based on high-fidelity data from a few locations. What if the situation is worse? What if there are other anomalies forming beneath the Pacific that we have not yet detected because of a lack of ground stations? The 70,000-year stall was a global event, but it likely started with local anomalies, growing and merging. We are currently watching the first anomaly grow. We do not know if others are gestating in the deep crust. The narrative of the Earth is written in magnetism. Every time the field flips or stalls, it leaves a record. We are currently writing the next layer of that record. Future geologists, perhaps millions of years from now, will look at the rock layer forming today. They will see the sudden spike in carbon, the radioactive isotopes from nuclear testing, and then, overlaid on top of that, they might see the signature of a magnetic collapse. They will see the start of the stall, and they will wonder how the civilization that existed at that moment coped with the loss of its shield. This discovery of the 70,000-year stall is a warning shot from the deep past. It tells us that the Earth's safety features are not guaranteed. It tells us that the core is capable of long, drawn-out failures. As we watch the South Atlantic Anomaly deepen, we must accept that we are not in control of this process. We can only observe, predict, and adapt. The magnetic heartbeat of our planet is skipping, and for the first time, we know exactly how long that silence can last. It is a silence that could stretch across history, reshaping the environment, the climate, and the future of every living thing on the surface. If you find this analysis of our planetary vulnerabilities valuable, please take a moment to like this video. It helps the algorithm prioritize scientific deep dives over sensationalism. We will continue to monitor the swarm satellite data and the sediment analysis as new findings emerge. The story of Earth's magnetic future is being written right now, and we are all part of the data set.